Right, the experiments for paper 2. The electricity ones, I've gone through mostly in the electricity revision. So you've got the electrical characteristics of either a bulb, like I've drawn there, or a resistor or a diode to draw a VI graph. So learn the setup, drawing the graph. If it's ohmic, it means V is proportional to I, it goes straight through. If it's a bulb, it's like an S. If it's a diode, it goes straight and then it goes up like that. Resistivity. You've done this one in class. You look at calculating the resistance by measuring current and potential difference, and you plot resistance against length, and that means that you've got a graph of the gradient is rho over A. Internal resistance, I've gone through in the other video. It's looking at E is equal to V plus IR. You measure V, you measure I, you plot V against I. If you plot V against I, the gradient is minus R, where R is the internal resistance. The intercept is E. Potential divider circuits, you can investigate them. You can use the thermistors and the light-dependent resistors to have a look and see what would happen to the potential differences across them. Okay, then on to the waves one. I'm only going to do a couple of these now and then we'll do the rest later. Using the oscilloscope to determine frequency. All you need to know about this with your oscilloscope, it gives you a time base. That tells you what the time division is between each of the vertical lines. Remember, they've probably got a millisecond or something in, so it might be 0.02 milliseconds. Then have a look at the wave that's formed, okay? The wave I've drawn there, can you see we've got one full wave, two full waves. Those two full waves take 1, 2, 3, 4, 5, 6 divisions. So I know 6 times 0.02, so that's 0.12 milliseconds is 2 waves. So I know that one wave would be 0.06 milliseconds for the time period. Then I'd use frequency as 1 over time. Okay, I've got to have a look a lot of these experiments, make sure I can tell you the right things, but the other things to be looking at: wave effects in the ripple tank, polarizing effects using microwaves and light. You've got another one about the reflection and total internal reflection, refraction, total internal reflection, superpositioning using sound, light or microwaves. You've got the double slit experiment and the grating experiment, and speed of sound using stationary waves in a resonance tube. So I'll have a look at that and try and get something together for Thursday. The Year 13 practicals, investigating capacitors in series and parallel, and also charge and discharge of capacitors, I've gone over in the capacitors video. The magnetic flux density using current carrying wire and a digital balance. That would be if we had a magnet, say we've got a horseshoe magnet like that with a north and a south on it, and we put it on top of some scales, on top of a balance. If we've got a wire, let's say that wire is going into the table there, can you see, using your left hand rule, if we've got the if we turn on the current, that wire would experience a force in this direction here. If the wire is experiencing a force in that direction there, Newton's third law says there's got to be an equal and opposite force. Well, that's going to be the magnets are going to experience a force on that in that direction there. Now, the size of that force you can find because whatever the reading was on the scales, if the magnets are being forced upwards, that reading is going to decrease. Now, whatever that reading is, say that reading comes out to be 0.021 grams, what we'd have to do is we'd have to work out what the force that would be equivalent to. It would be negative, wouldn't it? What force that would be equivalent to. So we'd use F equals mg, making sure, of course, that we had the mass in kilograms, G 9.81, find out the force. We then have that force is equal to Bill. We know the current because we'd measure it. We'd know the length because we'd measure it. We could find B. Okay, investigating magnetic flux using search coils. That involves having a search coil and moving it out of the magnetic field. And as you move it out of the magnetic field, you would induce an EMF. Now we know that EMF is equal to the rate of change of flux. Okay, so if we wanted to know what the flux was, what we could do was EMF multiplied by the time. The way we do that is we would plot a graph, maybe using a data logger, of EMF against time. So as we pulled it out, we would get some fluctuation. It might go straight down, it might go straight, it depends what speed we're pulling it out at. Then what we'd have to do is find the area underneath that graph. Investigating transformers, we did that in class. Remember that you'd need something that would measure the alternating potential difference or the alternating current on them, and that's just how you can verify the equation that the number of turns, the ratio of the potential differences is equal to the ratios of the number of turns. Absorption of alpha, beta and gamma particles, that's putting the different absorbers down, seeing that alpha would be absorbed by paper, beta by a thin bit of aluminium, and gamma will go through most things, it only gets stopped by lead. And determining a half-life of something, you'd have to detect the activity for however long, draw your graph. Okay, so you've got activity there, time there. Look to see when the activity fell to half and be able to read off what that time is. You'd probably then check it by the time it took again for that to fall to half. So I will go through some of these in more detail as we get through the revision, and I'm going to have a look over waves so I can make sure that we know all of those ones in a later video.